Olá, muito bom dia, você que está assistindo a mais uma Fraunhofer Quick Lives. Estamos aqui hoje com a presença ilustre, doutora Mônica Bosley, do Fraunhofer ISE, lá de Freiburg. E eu gostaria de dar as boas-vindas aí, a gente vai falar sobre um tópico muito importante hoje, que é na área de hidrogênio, né, o combustível do futuro. E espero que você goste dessa live. Eu vou trocar para o inglês para a gente conversar com a doutora Mônica. Hello, Monica. How are you?
Hello. Hi. Hello. I'm good. I'm good. How are you?
I'm fine as well. Thank you. Thank you very much for accepting to present some of your projects here at Fraunhofer Quick Lives. It's nice to have you. So, stage is yours. You can present yourself and then you can go already for the presentation. Thanks.
Perfect. Thank you. Yeah. My name is Monika Busil. I'm already 6 years now at Fraunhofer Institute for the Solar Energy Systems in Freiburg in Germany. And from the background, I'm a chemist. So I did my PhD in the catalyst development, especially focusing on the carbon-based catalyst for different hydrogenation reactions. And now, since last year, we are focusing as well on the dehydrogenation, but as well on the different liquid hydrogen carriers, considering the LHC, what I'm going to tell you later more a little bit about this, and as well considering as ammonia as a hydrogen carrier. But I would finish here, and more detail I will show you later on in the presentation slides. Oh, I think you're muted.
Share your screen. Yeah.
Okay, yeah. I can share the screen.
Yeah.
There.
Great.
So I hope you see my screen now.
You can see and then you can start.
Okay, perfectly. Okay, so yeah, today I would like to give you a short overview about the innovative catalytic systems for the efficient processing of the liquid hydrogen carriers. In order actually to successfully prevent, but as well to fight against the climate change, there are already a lot of activities going on nowadays, and not to mention that 6 years ago we signed the Paris Agreement in order to reach the limit, the target to limit the global warming below 2 degrees. And here, beside the Paris Agreement, where at the moment we have 191 states that have ratified the treaty, we have as well, for example, the climate neutrality agreement, which we want to reach until 2050. Here's, for example, Germany wants to be the climate neutral country until 2045. So we have very ambitious goals here. And as well, we have the global commitment to defossilization. So in order to avoid usage of the fossil resources. And all of these agreements and the goals are actually the drivers for global hydrogen economy. And this slide, as you can see, is a little bit messy, but here I want to show you that there are a lot of countries already globally which have the national hydrogen roadmaps, the different strategy papers, research and development programs on the hydrogen topic. Here, I'm not sure, but maybe later on you can correct me. The Brazil still doesn't have the national hydrogen roadmap, but last year I think you published a national energy plan where the one chapter is dedicated to the hydrogen technologies, and there is the clear message that the hydrogen technology will play a very important role and will have the impact on the energy market in the Brazil. And I think I don't need to mention that Brazil has actually very, very good conditions geographically, but as well from the meteorological side, to become actually the global leading hydrogen producer, but as well the exporter. At the moment in Germany, we have Fraunhofer Gesellschaft, who established in 2019 the Hydrogen Network. It is comprising 33 Fraunhofer institutes in Germany, and this network covers different materials which are applied in the hydrogen technologies, hydrogen production systems. It is considered as well the energy, industry and mobility sector, but as well the safety and the life cycle. Here we have two spokespersons. Professor Christopher Hebling from our institute. So our institute is here in Freiburg in the southwest part of Germany, and Professor Mario Rackwitz, who comes from the Institute for Energy Infrastructure and Geothermal Systems in Cottbus, here on the east side of Germany. At our institute, beside the hydrogen technologies and electrical energy storage, we have as well 4 other research topics. The main is as well here the photovoltaics. We have energy efficient buildings, solar thermal power plants and industrial processes, but as well the power electronics, grids and smart systems. Fraunhofer ISA, we have around 1,300 staff, including the students, and around 104.8 million budget. At our division, Hydrogen Technologies, which is actually very largely contributing to the Power-to-X technologies by three different topics. One of them is the water electrolysis. Here's our focus on the PEM water electrolysis and power to hydrogen. The second one is the sustainable mobility. Here we have the fuel cell cars. On this picture, you can see as well the fuel cell cars at our solar hydrogen filling station at our institute. And the second topic is power to X, where we have the synthetic fuels and thermal management topic. Here is very, very important, for example, in the scope of the synthetic fuels, OME or oxymethyl ether as a chemical, but as well as a synthetic fuel considered, and catalyst development for different thermochemical processes, and catalyst development for the liquid hydrogen carriers, such as, for example, ammonia or LHC. The question, why do we need catalysts? I'm pretty sure that all of you know that actually the future energy supply will be based on the sustainable feedstocks. And the green electrons produced from the water electrolysis can be then converted to the green hydrogen molecule. There is still demand how to store this energy or how to transport it. So demand is on the development for the hydrogen storage, hydrogen transportation technologies, and at the end, of course, we can use hydrogen directly as a fuel in the fuel cell car, or it can be used in the chemical industry in order to produce some advanced products, or, for example, to produce the synthetic fuels. What is here very important that all these topics, what I mentioned here, involve catalytic conversion. And actually, this is the reason why there is a need and demand for high-performance catalysts, and where we really need to consider the design, especially of the heterogeneous catalyst, the tunability of the catalyst properties, and on the long-time perspective, the replacement of the novel metal-based catalyst with the non-novel metals. So the renewable energy resources are actually time and geographically limited. And this is the reason why this energy storage transportation technology plays so important role. When we are considering storing hydrogen in the liquid form, we have here, for example, LHC technology. LHC means liquid organic hydrogen carrier, or we can consider to store hydrogen in the form of ammonia. Besides, in the liquid form, we can definitely transport very easily hydrogen in the gas form through the pipelines. However, when we are considering transportation of the hydrogen on the very long distances, for example, overseas, then is in the most cases economically more feasible actually to liquefy hydrogen or to transport it in the form of ammonia or in the form of the LHC. And here we are working on the LHC technology. What is actually LHC is the liquid medium where we store the hydrogen. So we have here the hydrogenation unit. We need a catalyst here. Then we transported hydrogen in the liquid form from the point A to the point B. And at the point B, we need to have the dehydrogenation process, meaning we release the hydrogen from this LHC carrier. An LHC carrier is used all the time in the cycle, so it is not consumed. Very important here is that this dehydrogenation step is very high energy demand. And here's actually the advantage of our technology, where we are collaborating together with Yeda Weizmann Institute from Israel, that we reduce this dehydrogenation temperature to 150 degrees. What is the huge advantage compared to the other LHC technologies, for example, where the dehydrogenation temperature is above 300 degrees. So beside the LHC, as I mentioned before, there is as well ammonia. Ammonia is synthesized through the Haber-Bosch process. We need here nitrogen and as well here green hydrogen. We transported the hydrogen in form of ammonia from the point A to the point B, and as well here is very energy demand process in order to release the hydrogen from ammonia. So we are so-called ammonia decomposition step, and this is actually the reason why there is a demand for efficient catalytic systems, especially in order to release the hydrogens from this carrier. In case of the dehydrogenation step in the LHC technology, or in the case of the decomposition step for the ammonia. So what is actually heterogeneous catalyst? It is the substance which is in the different phase than the educts. Usually the educts in the chemical reaction, let's say, are in the liquid phase. Then the heterogeneous catalyst would be, for example, in the solid phase. And the main role of the catalyst is actually to reduce the activation energy of the reaction, as we can see here in this figure, right? So this activation energy is actually without catalyst. It's much higher than, for example, with the presence of the catalyst. So the role of the catalyst is actually to accelerate the chemical reaction and to make it really economically feasible on the larger industrial scale, as for example here. And this is the reason why the heterogeneous catalysts are used in approximately 90% of the thermochemical processes in the industry. And they possess as well very large global market. Here I brought one example of the innovative catalytic system, which is based on the sustainable and tailor-made carbon-based catalyst. So here we are using the hydrothermal carbonization method, which is very simple, scalable, and the green technology. It is using the renewable biomass-based precursors, water as a solvent, and low reaction temperatures in order to synthesize this kind of the carbon materials. And because we are using the low reaction temperatures, we can quite easily tune the material properties of the carbon material. And by this, when we are applying these carbon materials in catalysis, we can as well tune the catalytic sites, which are actually the active sites in our chemical reaction. And by this, we can improve the catalyst performance. We can go beyond the commercial carbon-based catalyst, not only in terms of the catalytic performance, but as well in terms of the cost of catalytic process. So here is one example of the heterogeneous carbon-based catalyst application. I'm going to show you here in the LHC technology, which we are developing. Here we need catalyst in order to dehydrogenate our LHC carrier, which is in this case 2,6-lutetiene. And in order to store hydrogen, we need as well the catalyst, and 2,6-dimethylpiperidine is actually the loaded LHC Carrier. 150 degrees or even below is a temperature demand in order to release, but as well in order to store the hydrogen. This gives us possibility to use actually the solar energy to power this process. And beside this, this carrier is non-explosive. That means we can transport hydrogen in the non-explosive liquid form at a room temperature and atmospheric pressure. In this LHC carrier, we can store about 5.3 weight% of the hydrogen, and carrier has a wide operating temperature, meaning that even we can, during the winter when we have low temperature outside, easily transport hydrogen in the liquid form. It is very simple system because we are using the same catalyst for the hydrogenation and as well the dehydrogenation reaction. And this LHC project is so-called Storal H2 Project, so storing, releasing hydrogen. And here is the goal of Fraunhofer ISA. This goal of Fraunhofer that brings the technology from the very low scale or very low TRL level to the higher. And here's our goal to bring this technology to about TRL 4 to 5. So after 3 years of this project, we want to have this kind of the mini plant in Technicum, where at the moment we are still optimizing the catalyst performance, optimizing the reaction conditions. So beside the LHC, we are considering as well ammonia as hydrogen carrier. Of course, our motivation here is in the green ammonia, meaning that we are using green hydrogen to synthesize ammonia. Ammonia has a lot of advantages. It has very high hydrogen storage capacity, so approximately 3 times higher than, for example, LHC technology. It is carbon-free, meaning that we don't have any CO2 emissions via ammonia synthesis, of course, when we are using green hydrogen produced from the renewable energy source. And we don't have any CO2 emissions via ammonia combustion. Ammonia is very easy to store and transport because it is liquid at 20 degrees and 10 bar. However, it has some disadvantages. It is toxic and corrosive, and its direct usage as a fuel in the engine is still difficult. At the moment, the catalyst, especially for the ammonia decomposition, have low efficiency. That means there are still some tasks which needs to be improved in order to bring really ammonia as a hydrogen carrier in reality. Fraunhofer ISA is working as well on the production of green ammonia. Here has our process 3 main advantages compared to the conventional ammonia synthesis based on the Haber-Bosch process. We are using here green hydrogen produced from the water electrolysis, where the conventional Haber-Bosch process is using the hydrogen from the fossil resources. The second advantage is the integrated reactor concept, meaning we can in situ selectively separate ammonia. By this, we can shift the equilibrium and increase the space-time yield of ammonia production. And the last advantage here is the dynamic process operation, considering the feedstock fluctuation. Since we're using the green hydrogen from the renewable resources, is this actually very important. The conventional synthesis is based on the steady state process. And here's another application of ammonia reforming on board for the green shipping, for example. This is still our idea to apply our CatWeb technology, which was developed in our department in combination with a dual fuel ammonia with hydrogen, because actually hydrogen has very high flame speed, and hydrogen can by this accelerate the ammonia combustion in the engine, for example. Where the advantage of the CatWeb technology is actually, as you can see here, has very unique reactor design, where the catalyst support is actually electrically heated, and by this we can really onboard reform ammonia, and by addition of hydrogen we can then accelerate the combustion and we have green shaping without any soot formation and without any CO or CO2 emissions. And it is actually very important that beside the green or sustainable processes, we have as well sustainable catalytic materials. And here we are developing new non-novel metal catalysts on sustainable carbons for the ammonia decomposition, because at the moment, the state-of-the-art catalysts, as well, a lot of catalysts which are applied in the industry are novel metal-based catalysts, such as ruthenium-based, platinum, palladium-based catalyst. And here we want to replace this novel metal with non-novel metals such as nickel, iron, cobalt. And here is one example of the, this non-novel metal catalyst, which is supported on the nitrogen-doped carbon support. And you can see this, this light dots. These are actually metal nanoparticles, so our active species. And this shadow area is actually the nitrogen-doped carbon. And the advantage of the nitrogen-doped carbon is actually it's forming very good interactions with the metal nanoparticles, and its chemical structure is as well quite easy to tune, to change. And here I wrote one example of this nitrogen-doped carbon structure where we can see different surface functional groups. And by very easily, by heating this material to higher temperature, we can see here how the surface functional groups are changing. And this we can see actually by near ambient pressure XPS surface analysis. Here we have as well this device, which is since 2 years at our institute. And this is really a huge advantage, not only for the catalytic materials, but as well for some other materials applied in this energy transition technologies. And actually near ambient pressure means that we can go up to 20 millibar, and we can investigate the material up to 800 degrees in situ. So for example, we can see how the surface chemistry is changing by, for example, heating material. Or we can apply as well in situ gas dosing. We have different inert gases, but as well hydrogen or oxygen gas system. So to summarize, as you can see, we have very tough greenhouse gas goals. And it is very, very clear that one single technology will not do the job. So we need to consider all possible technologies, and we need to give opportunity, we need to develop them to show actually the advantages, or might be as well the disadvantages of the technologies. What is still required is the large-scale hydrogen production, global transport and trade. It is beginning slowly now, and in order to store all this this energy and transport it, for example, in form of the hydrogen liquid carriers, LHC or ammonia, these technologies needs to be really efficient in terms of the cost, in terms of the hydrogen loading and energy efficiency, especially when we are considering the hydrogen release, infrastructure which might be already available, logistic and ecology. And of course, to bring all these technologies on the higher scale globally, to use them, we need to improve the catalytic systems and we need to think big. So here I would like to thank you for your attention, and I would be happy to answer your questions.
So thank you, Monica, for this nice presentation. I have a lot of questions, but from my side, actually, as more as curiosity. But I would like to give the audience the opportunity to question question Monica. I'll switch to português. Pessoal, se vocês que estão assistindo aí quiserem fazer perguntas, podem colocar em português que a gente traduz simultaneamente aqui sem problema nenhum, tá? So, Monica, in order to begin with some questions, I have some curiosities. All these technologies that you have shown, they are on the middle of the technology until to the market. I would say the maturity level, it's not market ready, but almost there. This is the your work right now within this project, right? To bring
Yes.
these
Yeah.
technologies into the market. Can you
Yes.
explain a little bit more?
Yeah. I mean, it's quite hard to say, for example, for LHC or for ammonia, considering them as a high liquid hydrogen carriers, because there is still not this huge hydrogen production, so there is still not a market for this. However, for example, ammonia is, since, I don't know, 100 years applied as a fertilizer. So there is a market, but not in this case as a hydrogen carrier. And of course, the Haber-Bosch ammonia synthesis is used in the industry as well since, I don't know, 100 years. But ammonia decomposition, in order to get really high purity hydrogen, is still a little bit tricky. And there is still some demand for research to improve, especially the catalyst performance, because a lot of stuff is based on the performance of the catalyst, and later on the process development, definitely. But I would say the technology readiness is still not so high, and I think because the market is still missing, and on this side, the industry is more careful to bring or really to invest a lot of money.
Yeah. So I think
there was a lot. Disconnection.
But within this project that you already have, is it in Germany a big market? I mean, there are companies, small and medium enterprises, that are joining the project, that are being created in order to develop more the technology and bring it to the market. How is your vision with for this issue, I would say?
Yeah, I mean, we have several very big projects in the Germany, where a lot of industry is involved, but these projects are still financed through the government. So the industry brings maybe partially their money into, but not completely. And I would say, I mean, there are a lot of companies, for example, based on the LHC technology, we have, I think, 2 or 3 of them already. And the readiness level, I think, is very high there. So we are talking there really TRL 7, 8. Yeah.
Okay. Yeah. And regarding international market, have you guys have you been I would say have you have contact with a lot of industries from outside Germany, or for example in Brazil? We have contact on naturally because we have some research institutes that we are trying to connect to, for example, Fraunhofer ISE. But I mean, within the industry, you said that you have Israel already projects together, but outside I would say Israel and Germany, have you had any contacts from other industry, from other countries?
Yeah, there is a lot of going on with at the moment with Australia, Japan. These 2 countries, I mean, Australia has a lot of sun, so they can produce electricity really on the very, very cheap. And of course, they can allow to produce the green hydrogen and then to export it, for example, to Japan. And Japan is very very high level developing ammonia and as well LHC as a hydrogen transport medium. So there we have as well a lot of connections. For example, what I showed, this ammonia synthesis project, we are developing together with Japan, with the ICE Institute. And I must say that we have as well very good connections with Australia, with USA, with America as well. But with Brazil, as far as I know, there is at the moment, nothing going on. So we are still waiting.
But they'll come. They will come. We are working on this.
And I'm not sure. I was really checking for the national hydrogen roadmap. I couldn't find it, so I don't know if you have it.
We are working on it. There are some projects together with the Commerce Chamber of Germany here in Brazil, and also GateSet. This is a association for Zusammenarbeit, together, international work together, and they international collaboration. Sometimes the words they are missing, and they are together with the Brazilian government. They are working on it. There is the Brazilian Association of Hydrogen, and there will be something. There will come something, and we are also trying to connect just for you to know as well. And then we are trying to connect with also Fraunhofer ISE, and there will be some contacts sooner or later.
Perfect.
Don't worry.
Perfect.
Monica, we have a question from Juliano. I'll put here on the screen, but it's in Portuguese too, actually. How the institute perceives the vehicle application of the hydrogen in comparison to the electrical application?
We are considering both of them. I mean, I come from the division hydrogen technology, so of course we are considering the fuel cell cars, but in this bigger part of the institute, we have as well the battery technologies, and we are considering both of them. And this is definitely. Some people are saying, it does not make sense to develop the hydrogen cars. But of course, as I said in the conclusion, each technology will find its application. As well, the electric cars will find, or they are already applied, and it's going very well. But for example, the fuel cell cars would be most probably for the trucks, for the long distances, and so we're considering both of them.
Okay, great. He mentions that in Brazil, I don't know if you know, we are facing a huge electrical crisis because our energy matrix is made of hydroelectrics, and right now there is a period of huge dry. We don't have enough rain period. We are a little bit running out of water in the reservoirs. That's why. And he's mentioned that once we have this problem with the electricity, how to provide electricity, how to supply for the cars and vehicles, we also have to supply to other sectors. And how could you get over it? Can we surpass this problem? And as you said, I think the fuel cells are one of the solutions for this. And I know that in Germany, we Fraunhofer, we developed a national action plan for the Brennstoffzellen, and the production of fuel cells there. This is interesting. This is really interesting. And as you mentioned, it's nice to see that Australia is bringing something together with Fraunhofer. Japan, we know that's because of the high technology. But I really believe that Brazil will be the biggest producer of hydrogen in the world. We have, I think, the biggest potential of biomass and biogas generation and other also sources that are also green, that it can also help the world to get all of this crisis of the CO2 and other greenhouse gases, right? I think Brazil, you're really on the top with the biomass research topic. It's amazing how strong is biomass in Brazil. Definitely. And we hope we are doing something sooner with Fraunhofer ISE.
Yes. I mean, we tried already once, but the topic was a little bit far of our research topics. And as you probably noticed already, the hydrogen is really, this is a lot of new projects, a lot of work going on. So they keep us very busy. Yeah.
Yeah, this is true. Monica, I think we are already coming to the end. So I'd like to thank you very much for your presence, your presentation here.
You're welcome.
This lovely talk, and I hope we get in touch sooner and
definitely
later, soon enough. And I'll switch right now to Portuguese. But thank you very much again, and for your time, and also for your
for you.
Congratulations on the projects that you are performing right now. It's nice. It's nice to see that.
Thank you.
Okay. Pessoal, agradecemos mais uma vez aí a presença de todos. Gostaríamos, assim, se vocês tiverem dúvidas, contatos, quiserem entrar em contato, falem com a gente também. A doutora Mônica Bosley, ela também dá a apresentação, a gente vai deixar lá na nossa página da Fraunhofer Liaison Office no LinkedIn. Então, quaisquer dúvidas, por favor, entrem em contato. E desejamos a vocês aí uma ótima semana. So, bye-bye. Até a próxima.
Bye. Ciao.